Okay, so, ladies and gentlemen, we're now on the third part of exercise 5. We're being asked to create a function, parameterized in whatever way, that returns a stream of long numbers, where each element of the return stream represents successively larger prime number. Prime numbers being these numbers that are not divisible by anything except 1 and number itself, right? And so this is going to be a stream giving successive primes. However many primes we want, it will give them to us. But the rest it will hold behind the scenes in a potential form. It's kind of like potential energy versus kinetic. We hold them in potential form. It knows how to compute more upon demand, and will produce them to us. Okay. And we are going to follow some similar techniques to what we used above. And as above, I will show 2 ways of performing this. So one way is a little bit of one way, as with the other examples. Sometimes we could do it in ways that exploit some of the more finesse of Scala features. Others are more straightforward conceptually for those not as familiar with Scala. So I'm going to start with the more straightforward ones. Okay. So we have to define a function. So what should we start with? Def. Good. Def. Okay. Generate primes. Oh, I admire any contribution. Let's take advantage of the lack of 2-second delay. Okay. What is it going to take as arguments? Okay. What should it take as arguments?
Stream of lines.
Okay. You're great. That's awesome. That's exactly right. So you folks are doing better than last year's students. So So we had a sort of almost primes last year. It tried, but it didn't quite get there. And actually, it's useful to explore those. Okay, so stream of longs. Okay, so this is like a candidate, like n. We could call it n because we're trying to actually understand is n a real prime or not, and then the primes thus far are previous primes, sort of previous ones which we know are primes that are smaller. And we're going to, and what is the type of this function going to be? What is it going to return? A what? Stream of long. Yeah, there it is. Okay. But, so this is one way to do it. It's not the only way, but it's one way. Okay. And this reminds us of the sieve of Eratosthenes. For those who know the history of mathematics or are students of classical Mediterranean civilization. Okay. Okay. So if we have the primes thus far, the primes prior value less than n minus 1, and we have this candidate, what could we do that would help us determine if this number is a prime, the candidate? Okay. 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 And we could do that.
I use a little different. First, I didn't use all these parameters.
Okay.
I used 2.
Okay.
And I used map.
Yeah.
So I build a string from n to, from 1 to n. And then I use map. I take the module. And I check if this module, I have 2 zeros.
Okay. Okay.
And the zeros are
Exactly. Yeah. Yeah. So if there are at least 2 zeros, yeah. Because you know, one of the numbers in there with 1, it's going to go and it's going to go. Yeah. Okay. So that would be a way to do it. I filter. Yeah. So what should we filter?
Filter for the hash. I also have a string from 1 to n. And for each number, that I filter anything which can be.
Okay. Okay. Yeah. So it's a very similar idea here. Okay. So I'm going to show you one solution which uses filter. Okay. So here's the deal. We're going to filter out for the primes thus far. We're going to filter out ones that are too big to possibly divide ours. How do we know if it's too big? Yeah, it's greater than the square root of this. So what I'll say is if primes thus only retain those that are such that they fall within such as their square is less than or equal to this candidate. Okay, because I mean, suppose we're looking at a candidate of say 10. We want to know it's 10 prime, right? We don't need to examine 5 if we've already examined 2, right? So here we're going to do filter, okay? So we're to sort of marshal our efforts to focus them on sensible ones. We know if there's one less than the square root that we're dealing with, it would have to be paired with one greater than the square root. So we don't have to check all of them, right? If those that are greater than the square root, they would have to be multiplied by something less than the square root, okay? So we don't want to sort of do more work than we have to. And then I'm going to ask, for those that remain, does there exist one, okay, where does there exist a value where the candidate mod that value is equal to 0? Do you see that? Do you understand that? So in other words, for those primes that are less than or equal to the square root, do they evenly divide this, right? Okay, so here, now I've written it out in a way that makes me think that maybe I need to. The question is, do I want to live dangerously? I think not. Why don't we do it in the same way I've written down, and then we can explore if it's needed. Scala's type inference sometimes is imperfect, to say the least. Okay, so I'm going to say, okay, so we're going to ask here, is candidate mod this prime equal to 0? Okay. If there exists one for which it's equal to 0, then we know basically candidate is what? So suppose there does exist one for which this thing is equal to, there's a previous prime which the candidate mod that prime is 0. Then what does it tell us about the candidate?
If it's 0? No,
yeah.
It's not a prime.
It's not a prime. So in this case, ladies and gentlemen, then what is the stream of primes next element? Well, or what is the stream of primes that we should return? Well, it's just the stream of primes that result from candidate, considering candidate plus 1. So let me write it out, and then you can ponder it. Generate primes, candidate plus 1, comma, primes thus far. So do you see what I'm saying? So if candidate is not a prime, then the stream that we have to return, it's just the list of all primes really less than or equal to candidate. It's just, excuse me, of all primes is the stream of all primes that results from this next call where we're considering candidate plus 1. And we have no new primes to consider because we haven't found a new prime. So it's just primes thus far. Do you see that? So in other words, candidate is not a prime. So if we want to generate primes, you know, considering candidate, well, we know it doesn't have to be part of the list we return of primes. And in order to compute the remaining primes, we don't have to pass it up because it's not a prime. Do you see that? Okay. And then I'm going to say else. Okay. Suppose we're here. What must be the case then? We're in the else clause. What must be the case?
Prime.
It's prime, ladies and gentlemen. So for this list of primes that we're returning, what must be the first element of that list? Candidate. I heard it whispered. And we can append that to what? Generate primes. And what's the first argument of generate primes? Candidate plus 1. And is it just primes thus far, though? Candidate constituent primes thus far. Thus far. Okay. I said somehow that I said V. Oh, did I not? Oh, that's weird. Okay. Mumble. Okay. Fine. I'll just go paste it. I ladies and gentlemen, I did not properly take. What do I have to do here? What did I forget?
Name the V parameter.
I need to name the V parameter, ladies and gentlemen. I need to name the V parameter. So V, and just have friends that make clear what this is, okay? And then if that is the case, then, sorry, then generate the primes like this, boom. Okay, boom. And let's give it a nice indentation. Oh my gosh, oh, what's going on? Oh, I forgot the curly bracket. Oh, this is horrible. I should be inside Zeppelin, and now I've abused your trust. Okay, there we go. Okay, now we'll go and paste this down here. You folks are living the charmed life inside of Zeppelin, while I'm in the nasty, brutish, and short life of the Scala interpreter. Okay, there we go, and we need that final. Okay, come on, we need this line. Boom. Okay, and there we go. There we go, and there, and then like that. Boom. You see that? Okay, now, ladies and gentlemen, we've just defined this function. Will you forgive me if I say I'd like to look at some prime numbers? Okay, forgive me, but I will exercise it now. primes equals generate primes. And I'm going to give it, now this next argument is very important. What do I give it as its first argument? 2. If I gave it 1, why would that be a problem? Yeah, well, because it's going to be taking each number, each candidate mod 1, which is not going to be helpful because it's going to be, I think it's probably going to be defined as 0. I'm actually not sure what happens. Maybe it blows up on you. Okay, and an empty stream. Here we go. Primes. Are we ready? Are we ready to see these? Okay. Take the first 5. When you're dealing with streams, treat them with respect. Treat them with respect. Okay, take 5 and then force them, right? Okay, so far so good. Looks good. Let's take the first 10. Take the first 100. Do you see that? Indeed. Okay, here's my generate. Oops. I just wanted to show you my generate primes again in case you wanted to see it. Here it is. And it's here it is. In its fulsome glory. Okay. There it is. Right? So in short, we take a candidate that could be prime. We're trying to investigate if it's prime. We consider the primes thus far. For the primes thus far, we filter them so that those that are bigger than the square root of the candidate get filtered out, so we don't do double work. Right? We only consider, like for 10, we only consider 2 and 3. We don't consider, those above 3 point whatever. So we don't have to consider, for example, whether 4 or 5 or 6. Excuse me, those aren't primes. But 5 or 7. Divide it, right? So we to sort of spare ourselves work, we filter out some that are too big, and then for the remaining ones, we ask, okay, do they evenly divide the number, right? If they evenly divide it, we know it's not prime, and therefore we don't have to return it in our list of primes, right? And we know whatever primes there are out there, they're the ones that will be returned by whatever primes there are from this point onwards, from candidate onwards, including candidate, are the same as the primes from candidate plus 1 onwards, with just the primes thus far found. By contrast, if candidate is prime, we append it. The primes from candidate onwards include candidate, right? It's prime. We found it's prime, and whatever primes are found from candidate plus 1 onwards, considering the fact that candidate itself is a prime in the number to do there. Do you see that? Takes your head a little bit of time to get your head around that, but who could deny beauty? Yes.
Well, I'm not denying beauty, but I'm just curious, is it ever the case that primes thus far will contain a prime that is too large if we're starting from 2 and working our way up?
Good point. Good point. So that it's too large. In other words, so we're starting with candidate being 2, right? We're started with candidate being 2, yeah? And you're saying, is it possible that what?
Is it possible primes thus far will contain anything that is larger than the square root of the current candidate?
Hmm. No.
Well,
I think
it may be possible.
I think it's possible.
I can't do the math.
Well, let's think about if it's examining. If it's examining 7,
Yeah,
primes thus far would include 5, for example.
yeah.
And,
Right.
and so that would be a case where primes thus far, it would have accumulated 5 along the way. And so there would be something filtered out by this test.
Yes. Okay.
Yeah, because 5 is greater than the square root of 7, which is somewhere like 2 point mumble. So, and 3 would be also, right? 3 would also be a prime in primes thus far when considering 7. Yeah.
In terms of tractability, does that become significant when we get to pretty large primes?
It's a good question. Well, we are filtering out those that are above the square root. So we're not systematically doing the modulo with respect to them. This filtering, though, is going through each and every one. What would be really nicer is if filter knew the primes are in a certain order, that they're ordered, the primes thus far, it could be much smarter at stopping at a certain point, just saying from now on they're bigger than they need to be. But it goes through the entire list, and so that's actually approximately, it's a considerable waste there. I don't know in Scala if there's like a filter for sorted lists that allows you to sort of be more intelligent about that, but I would think that would be a cost. So it's a good question. I want to think about it. Now, other questions about this before I show you one that is recommended by Beauty and Brevity. Okay, do you want to see Beauty and Brevity? Okay. Okay, well, I'm glad no one said, no, I want to go home. Oh. Okay, here we go. Okay, now this one uses, as I alluded to, it uses special finesse in Scala. Lazy values. Lazy prime stream. Let's call it, lazy prime stream. This is a stream of, now, I'm sorry here, but I'm going to make this a stream of ints for simplicity, okay? Otherwise, we have to do more. Okay, it starts with 2. Const on 2. Watch this. Okay, stream dot from 3. What does that give us? What does stream dot from 3 give us? 3, 4, 5, 6, etc. Dot filter. Oh my gosh, there it is. There it is. I answered my question. Prime. Okay, so we're going to filter out numbers I. Only include numbers I that match the following predicate. At prime stream dot take while. Okay. Yes, this is how you do it. Oh, that's cool. Okay, yeah, take while, ladies and gentlemen. Take while will get all the elements as long as the condition is a predicate is matched, it'll get all the ones up to that point. So if it's a sorted list, it will allow you to kind of go up and only get those to a certain point in the list, rather than, say, filtering for also take while. We have K. This is a K for candidate. Okay. Okay. Okay, actually, no, it's not a candidate, but it's a prime number. And we're testing if K squared is less than or equal to I. Okay. Probably to be consistent, instead of calling it just I'm going to call it candidate. And here we go, candidate, ladies and gentlemen. Candidate. Okay. Okay. And let me make sure my parens are matched. Believe me, if you work in Lisp, you got to be especially attuned to that. Okay. And then I'm going to say for all. So I'm filtering for just this list that are within this, that are less than or equal to the square root of the candidate. I'm testing if for all of them, I'm going to call it P. I don't like calling it K. I'm speaking to myself there. Okay, if candidate mod P is greater than 0, there we go. And I'm going to go back and I'm going to rename the K to a P because it's a prime. After all, it's a member of prime streams. Okay, so what am I doing here? Basically, I am taking all the primes to this point. I'm filtering out to only consider those that are less than or equal to the square root of candidate. And then I am testing if for all of those candidate, when you take candidate mod that prime, it's greater than 0. Do you see that? Now, there may be something that disturbs you about this. Is there something that disturbs you about it? Is there something that's a little bit odd here? Where is this prime stream defined? We're defining it in terms of prime stream. Isn't that awesome? It's recursive. Okay, now watch this. Let's see if this works. Okay, prime stream dot take 5 dot force. Is that awesome or what? Ladies and gentlemen, prime stream here is a stream of events. It starts with 2. And we're going to append to it something. What are we going to append to it? We're going to append to it, well, for all numbers greater than greater than or equal to 3, we're going to filter them to only include those for whom prime stream does not include a candidate for which this is greater than 0. Okay. In other words, we're going to filter. We're going to filter to only include those which, when we consider all previous primes, they don't divide this number. Okay, as the previous primes being these ones in these prime streams. So we are adding to prime stream over time successive values for which previous values of prime stream none of them divide evenly into it. They would divide evenly into it if candidate mod P equals 0. If none of them, that's why I say for all here, is for all predicate. If for all elements of prime stream computed thus far, none of them divide this candidate value from this stream, then we'll retain it. And all the previous elements of the prime stream are, well, they're prime. So we'll consider this a prime if all the previous elements didn't include it, right? And the reason it can be recursive is because this is lazy. So it only evaluates it when needed. Okay? So it is defining itself incrementally based on its previous values. Do you see that? Do you see that? Nice, or not. Bit of a head scratcher, but it's defining itself in this incremental way and using its previously defined values to filter the elements of sort of future primes, so to filter out those that previous elements of prime stream evenly divided. Do you see that? I think I discovered this in class last year. I said, I wonder if you could do that. And it turns out you could. It was awesome. Okay. There is rightfully hushed silence, and I will not disturb that.
Hey, can you take 1 million elements, 1 million prime numbers? I could have done it with the main ID.
Okay. Do we really want to challenge the?
Why streams are so slow? I found some implementation on the internet.
Yeah.
Using iteration.
Yeah.
It takes probably less than 100 milliseconds to generate 1 million elements.
Yeah. Here's a million. This is casual observation would suggest it's more than 100 milliseconds. It's recursing down and filtering and so on. The interesting thing is there's no function here. In that definition, there was no function, right? This said no function in it. It was just a lazy value. It's still working hard. Still working.
It's very beautiful, but slow.
Yeah, it'd be interesting to know what's going on. Yeah. It could be. Well, one of the things it's actually. Well, we'll talk about that next time, because in 5 minutes I have to introduce a guest speaker for my software engineering class from industry. So I apologize. Christine is out sick today. There it is. There it is. And with that thing of beauty, I will close, ladies and gentlemen, this component of the lecture and the lecture. Thank you, etc.